Okay, so I want to start by thanking Rita Ribeiro. It's a pleasure to have you here today to talk about a subject that I think it is very interesting and relevant at the moment. Rita Ribeiro is an assistant professor at the Department of Computer Science, Faculty of Science, University of Porto, and a researcher at Riyadh in ESCTech. She has a PhD in computer science from the University of Porto, and her main research topics are imbalanced domain learning, outlier detection, evaluation issues on learning tasks, and problems related to social good. She has been involved in several research projects concerning environmental problems, fraud detection, predictive maintenance, and so on. She has been a member of the program committee of several conferences, reviewer of several international journals, and organizer of scientific events. She is also the director of the Master in Data Science at FCUP. Rita, once again, thank you for accepting our invitation, and you may start whenever you feel like.
Okay, Eduarda, first of all, I would like to thank you for the invitation and for being able to present one of my research works and research lines. This is basically the presentation of a published paper along with Nuno Muniz on some topic that I have started with back with my PhD, and very slowly we have been working on this issue. So I will start by giving you some brief motivation for this problem, which is imbalanced regression, why it is still challenging, what kind of problems can we face with, and so forth. So basically, whenever we are in a scene of a standard predictive learning task, we assume that all the instances have the same value for us, okay, the same importance. So if the cases are equally relevant, then we can assume that all the costs are also equal. So the thing is that if we assume that our learning algorithm, whatever that might be, will focus on being especially accurate at most frequent cases, because he's searching for an overall good performance over the domain. But what happens whenever we are trying to learn from an imbalanced domain setting? So in that case, we can no longer state that all the values across the target variable domain have an equal importance, and there are few of them that are more relevant than others. Moreover, they are usually rare within the target variable that we have. So accordingly, if they are more relevant, the costs of making an error on those specific cases should be higher than the ones made at most frequent or less relevant values. So we have been seeing research for over more than 2 decades on this topic, but mainly on classification. So we have the cases of problems of imbalanced classification problem, especially binary imbalanced classification problem, where the goal is to predict what we call the positive class, which is also the minority class. Examples include things like fraud detection, rare disease diagnosis, and so forth. What happens with regression? Regression, there are a lot of applications that in fact have such property as well, but within a regression context. So in those applications, there is usually a specific range of the target variable that is scarce or scarcely represented, but is of highest importance for the domain, okay? And usually those values are typically at the tails of the distribution, so are extreme values. And making predictions at those values is more critical than the remaining cases of a more average target variable. That can be the case whenever we have applications of extreme temperature values, high energy consumption demand, and so forth. Many, many scenarios. And why is that far more research exists in classification if we compare to the amount of work that exists in regression? So basically, our idea is that the gap exists because of two main issues. One of them is it's not easy, not straightforward to define this non-uniform preference over a continuous domain, okay? So here, our idea was to build up a so-called relevance function that is obtained through a method that is automatic and non-parametric. And I will tell you in a moment how that works exactly. Then the second challenge that such contexts in regression pose is how can we properly evaluate the models within this scenario. So in classification, we know that whenever we have an imbalanced predictive task, standard metrics such as the accuracy are not appropriate. The same happens with the regression. So standard metrics like the mean squared error or the mean absolute error or so forth are based on try to enhance the performance of models over the average or the median target values. So in the case that we have an imbalance regression problem, the idea is to have a metric that is able to some way reflect our preference bias, so that we want to express how good our models at predicting those extreme values, but without disregarding all the values of the domain, okay? So we want an evolution metric that is robust to severe model bias as well. So where are we at? Basically, we have three main aspects that we can say that define an imbalanced domain learning problem. So if we look at the target variable distribution, we would say that, okay, we have an imbalanced target variable distribution. Regarding the domain preferences, they are not uniform, so it's not equally relevant all the instances. And moreover, where is our predictive focus? So in the case of an imbalanced domain learning, we would say that our focus is on the rare cases if we talk about classification, or the extreme values if we talk about regression. Of course, this is an even harder problem if we have some case of data difficulties that usually make this problem hard. So I have here a simple example which shows you where these kind of problems can emerge. So we have a air pollution example where we have here, I have fetched a data set that has the concentration of a pollutant in Oslo for 2 years. So this is a well-known benchmark data set. And I have also fetched the World Health Organization directives regarding the concentration values that are admissible for that pollutant. So here on this line here, I have signaled the limit threshold. So this 5 here, which is basically the threshold above which the World Health Organization states that it's harmful for human health. Okay, so even though they are far less frequent, we would say that it would be much more useful to find a model that, even though here may fail by a little bit on the prediction of these concentration values of this pollutant, we want a model that is especially accurate around these values here. Okay. So, but how can we now define these non-uniform preferences on the target variable? So back during my PhD, I have proposed, along with my supervisor, Luis Torgo, a relevance function, which is basically a mapping of the target variable domain into a relevance space, which is bounded in the interval from 0 to 1, where 0 is the minimum relevance and 1 is the maximum one. So, but how can we obtain such a function? Okay, so given the infinite nature of the target variable in a regression context, we cannot state or define a relevance value for each possible value. So it's infeasible, contrary to the classification scenario. So we would like to have some kind of approximation that would allow us to build this continuous relevance function. And the solution that we found by that time was to resort to a specific interpolation method, which is the piecewise cubic Hermite splines, that it's able to, given a set of control points and the derivatives of those control points, we can interpolate and make or supply the information that is needed for inferring this relevance function. So I will get back to the pollution example, and I will use the World Health Organization directives as what we call the control points. So basically, let's say that this is the maximum relevance value. So it's the limit above which it's harmful. So we want our model to be especially focused at this point. And let's state that low concentration values and the annual mean guideline have no relevance. So what our interpolation method does is, by assuming I also supply here the first derivative, and I'm establishing these control points as local minimum or local maximum, but I can also play with that. So let's assume that they all have first derivative equal to 0. So we have here the local minimum and here the maximum. This interpolation method also ensures that we will not get out of these values of this range from 0 to 1. So if I supply this to my interpolation method, he will build up a relevance function such as this one. Okay, so I gave the values for here and here and here, and it smoothly interpolates these values. But what's the problem with this simple approach? Is that most of the times we don't have such domain knowledge that allows us to state, okay, from this point on, it's dangerous, and in that point on, it's not dangerous, and so forth. So we needed some automatic way to infer this relevance function based on the target variable distribution. And what it was proposed back then, it was also a method that used the box plot to extract such control points in an automatic way and provide it to the building of the relevance function. Here, we have made a small adjustment, and we use what we call adjusted box plot, which basically is a box plot that gives us a more robust measure of the skewness of the distribution. It is not parametric as the standard box plot from Tukey, and so it's more flexible, not assuming this underlying distribution as a fixed one. And by using this adjusted box plot, we can take the exact same target variable and ask the method to build up a relevance function, assuming that across the extreme values are the most important ones. Moreover, here in this specific domain, we are specifying that the high extreme values are the most important ones. We can either specify that they are higher, the higher are the most important ones, the lower, or both of them. By default is the both of them. In this particular case, we are of course interested on the most harmful pollution concentration values. So we specify that we want only the high extreme values as the most important ones. Okay. I have made here just this to give you a notion that, of course, this automatic method depends on the representativeness of our data sample. So if we take the same kind of, this is another pollutant, this is PM10, but it is well known that this pollutant have different, as a different distribution with respect to different location in the planet. And here I have made just an example of the same kind of pollutant taking out from Beijing, Oslo, and some rural station in Germany. And here I have the domain knowledge relevance function. Okay, it obeys those strict World Health Organization guidelines, and so basically it's always the same shape. And on red there are the relevance functions that are inferred from this automatic method. Okay, they are clearly different, but maybe what is a concern in one data set should not be a concern in another. Well, but that might be arguable. But what I want to say, of course, that depends a lot on how representative is our data sample regarding the domain. Okay. So that gives us a tool to define these non-uniform preferences. But now we have another challenge. How can we evaluate the model in such an imbalance regression context? So we would like to have some way of, or some metric that allows us to select the best models, but also we would like to embed such evaluation metric in the process of model optimization. So let's start with the problem of standard evaluation metrics, and back in the same example, I have made some two artificial models here, M1 and M2. They are made in such a way that they have exactly the same mean squared error, okay? But should they be equal from the domain perspective? So what if we look closer to the predictions made by M1 and M2, we see that, okay, M2 does big errors here and smaller errors here, and M1 is on the opposite direction in the sense that, okay, it's very accurate at this region, but it misses for a lot here. So they should not be equal. not if we look from the domain perspective. So basically, it would be more serious to have such big errors in these more critical air pollution concentrations than having these errors regarding what is usual or standard regarding these concentration values. So from the domain perspective, they are clearly different. And we need to have some way of distinguishing these two models. But we would like to distinguish them without having no strict threshold, okay? Because I could say, okay, I want to see what is the most accurate model from this point forward. But the thing is that we have a continuous nature. We are in a regression context. So we would like for him to, or the metric to consider all the prediction errors along as we move with relevance going higher, okay? So the higher the relevance, the higher the cost, if we wanted to tell it like that, of the errors committed at those values. So if it's stated that these standard metrics, such as the mean squared error, are not suitable, how can we build up an evaluation metric that would answer the following things? So we want a metric that focus on minimizing a specific errors on a specific range of cases, which in this case are extreme target values. We want also that measure to not have a severe bias regarding those extreme values. So it would not be very useful also to have a model that is very good at those extreme values, but is awful or very bad regarding all the remaining cases. So we don't want to just disregard the remaining cases, but we want to account them somehow. We want to reflect this relevance as an importance factor for the errors, okay? Our metric that I will present you next also provides us a visual way to discriminate, compare, or select the models. So first, the math part. What basically we have proposed is we have a data set and we have a given relevance function, okay, which is obtained by the automatic method or by some user domain or user supplied control points. We define that a subset of this data set, it's this DT, if we consider all the instances for which the relevance of the target variable goes above this threshold. So basically, if we consider D0 would be all the values in the domain, because all the values have the relevance equal or higher than 0. And if we consider D1 would be all the values that are considered outliers by the adjusted box plot. So they are subsets of the whole data set. And we define the sum of the squared errors for those sub-data sets. So if we want to define, the squared error relevance for a given threshold T would be the sum of the squared errors for all the points that fall in that sub-data set, okay? The intuition is this one. So, but that is as an interesting property, this squared error relevance, because if we, given that this relevance function is bounded, so it's within the interval of 0 and 1, we know that as we increase the value of T of this threshold, you are accounting for less and less cases, okay? So we know that if each point of SER would be, the maximum would be obtained for t equal to 0, which is all the points. And as we increase t, less and less cases are accounted for this overall sum of squared errors. So if we build up or join all the points or lots of points varying the value of t, we will end up with a curve that is decreasing and monotonic. So basically, we obtain this. So before going into details here, so here we have point of SER for the threshold of relevance 0, which is basically the sum of squared errors. And as we move along the x-axis here, we are increasing the threshold, which defines which are the cases which should be accounted for the sum of the squared errors. So ultimately here we are accounting only for the errors committed at the values which have the maximum relevance 1. This point here is the cases that sum of errors that have relevance function above 0.5 and so forth. And why is this interesting? Because if we take the area under this curve here, we have an estimate of the performance of the model, giving more emphasis to the highest relevance values. Why? Because if we look here, all the relevant maximum relevance cases are accounted here, and they still are accounted more and more times as they are more and more relevant. Or if you wanted to put it in another way, the less relevant they are, the fewer times they are being discarded. So for instance, the relevance values that have a relevance of 0 are accounted only once, okay? And this gives us the nice intuition about the overall performance of the model, with a special emphasis on the most relevant ones, but without disregarding all the target variable values. So basically our proposal is the squared error relevance area, which we call SERA, which is basically the area below this curve. And I will show you briefly what we aim to show regarding the capabilities of this metric. So we would like this metric to see if this metric is really able of performing some model selection according to our goals. And the other thing is the possibility of this metric being appropriate for model selection. So we have a set of data sets with extreme values that we have fetched. We have just chose 5 algorithms and performed some grid search of hyperparameters and perform a cross-validation. And our first question is this metric able to reflect properly, according to our goals, the best models to be selected? So here we have just 3 examples with 2 models. And what we have here is basically the green lines are represent the models that are selected by the mean squared error. And the blue ones are the models that are selected by the SERA metric. So what we see here is, of course, that the models that are selected by the mean squared error have at relevance 0, which is accounting for all the target variable values, always the lowest sum of squared errors, okay? But as we move along and our threshold for the SER increases, so approaches 1, we see quite different behaviors of the models, okay? So here we have a model that started at the same point of the model that was selected by mean squared error, but we see that regarding the Serra metric is also smaller, making smaller errors as we move along the increasing of the relevance values that are accounted for each point of this curve. Here we actually see some turning point, which is okay at the beginning. That would not probably be the model that would be selected, but from this point on, it in fact shows a better performance than the other one. And here we have an even more extreme, if I would like to say like that, situation where in fact this model here is much better accounting for the extreme values without disregarding the performance and all the remaining ones. So that happens because, of course, the mean squared error accounts for the highest density regions of the target variable. So they are basically focused on this point here only. Okay. The next question is that if we can use Serra as an optimization loss function to be included in the machine learning algorithm. So at this point, we didn't make any specific study on that respect, but we wanted to know somehow if it would be a good metric where we could in fact play with this optimization procedure. So what we did was to take the data sets, split and train and test. We have considered two optimization parameter methods, and out of that optimization, we select the best model and train on the using the entire training set. And then with those models, we have made prediction on this out of sample partition. So what we would like to answer is if the models that are selected by the optimization process and by the out of sample are really practically different, okay? So that the notion of the practical difference is related to the Bayesian approach to comparing models, and we resort to the Bayes sign test to assess that practical difference between the models. So we take the difference of the Serra scores obtained by the models that were selected by the parameter optimization process and by the out of sample estimation. This Bayes sign test, this Bayes sign test has some what we call a region of practical equivalence, for which the two models are considered practically equivalent, and then they are the remaining parts of the out of those interval where we can state that actually the model is practically better or worse than the one that we are comparing. So here we have on these graphs are the results of that comparison. So we have the Serra of the algorithm that was optimized in the sense of it was done a grid search or a hyperband search for obtaining the best parameterization possible. And we subtract from that the Serra of the out of sample estimate. So what we noticed is that, of course, if this difference is negative, it means that it actually is worthwhile to work on the optimization, in the sense that the models that are optimized really achieve a smaller SERA score. So we are talking about errors, so the smaller the better. So that accounts for a win in the sense that it's out of the region of practical equivalence. If the difference or the percentual difference is within this rope interval, we would say that they are practically equivalent. And we say that, okay, it's not good to try to optimize SERA if in fact it's worse than just obtaining in comparison to the SERA obtained on the out of sample. What the results have shown us, so this is regarding all the data sets that we have run, is that the optimized models are of practical equivalence or outperform the out of sample models with more than 50% of probability, okay? That is an indicator that SERA, in fact, can be useful for performing optimization in learning algorithms. In fact, we have been working on such embedding, and the results have shown us that with SERA as an optimization metric could lead to better results with respect to our imbalanced regression scenario, okay? So basically, we have proposed a way to tackle regression tasks for the prediction of extreme values by proposing an automatic and non-parametric approach to approximate the domain preferences, okay? So a way of automatically supplying the control points to the interpolation function, and that is based on the adjusted box plot. And we have proposed a new evaluation metric, which is the SERA, which accounts for not only the prediction at the extreme values, but also the overall capability of the models regarding the target variable domain. So we would not like to have a severe bias in the models. Also, SERA allows us to have a tool, a visual tool to analyze the dominance of the models. So these are the references. So basically what I have present to you here was a paper with Nuno Muniz back from 2020. We have all these methods in a package of R, which we call IRON. We are working on, as I told you, the embedding of the optimization of SERA in machine learning algorithms. But we are still also working on a book, which is on imbalanced domain learning, which hopefully would come out at late 2022. So that finishes my presentation. I don't know if I went too fast, but I'm open for questions now.
Okay, thank you